Hello, Algebra 2 students. Unfortunately, I can't be with you again today, but you get to listen to my voice and follow along in your book. So please open up your books to page 202. Today we're looking at lesson 19 and we're looking at the end behavior of rational functions. So I want you to remember that rational just means that something is written as a fraction. So here's our warm-up. We've got a full long division all worked out with 2,775 divided by 11. And when we did that division, we get 252 and the remainder is 3. That helps us to figure out some of these other divisions. That's also written out right underneath it, right here. I have it written as 11 times 252 plus the 3 would also give me 2,775. That's just another way of writing that original problem. Or if I write that as a fraction right here for the division, 2775 divided by 11, I get that 252 as my quotient, my answer from the division. The 3 is the leftover, that remainder, and we can write that remainder with the 11 as our denominator for that leftover part. So these are 3 ways to just have the number way of writing that. And on the right side, I have these written as polynomials. And I want you to notice that the coefficients of the polynomials match with the numbers that we just worked out here. So instead of just 2,775, inside the division part, I have 2x cubed plus 7x squared plus 7x plus 5. That's the 2,775. And the divisor is x plus 1. It's 1x plus 1. That's where the 11 is coming from. So doing my long division here, they started it already. 2x squared times x plus 1. 2x squared times x would be 2x cubed. And 2x times 1 is 2x squared. I don't know if I said 2x squared. And then we subtract, but then you know that we're going to do add the opposite, and this cancels. 7x squared plus a negative 2x squared is 5x squared. And we bring down our 7x. And then I would ask, what do I have to multiply the x times to get to 5x squared? And that would be 5x, which makes sense. Remember, we're going to get 252. So we've got our 2x squared and our 5x. So when I multiply 5x times x plus 1, I'll get 5x squared. And 5x times 1 is 5x. And then we'll do our subtracting, but we'll really add the opposite. This cancels. 7x and negative 5x is 2x. And we'll bring down our 5. And then what do I have to multiply x times to get 2x? That's 2. And again, that should make sense. 2 times x plus 1 would be 2x plus 2. When we do our subtraction and add the opposite, it shouldn't be a surprise that we're going to have a remainder. The 2x goes away. 5 plus negative 2 is, there's our remainder of 3. And we've talked about how we have remainders sometimes when we do these kind of problems. I know I kind of ran into the next problem, but that remainder of 3 we can write different ways. Sometimes we just leave that down at the bottom, just like we're going to do on that one. For the next problem, thinking about what we have right here, that 2,775, and how we can write that polynomial split into factors. I'm just going to write that 3 a little bit smaller. That could be written as, again, looking at what we've got over there, instead of 11, I'm going to have x plus 1. And that could be multiplied by 2x squared plus 5x plus 2, thinking about what we just did with our division. But we also have that remainder. And that remainder is going to be the plus 3, just like we wrote it over here. Okay, it's just that we're writing it as polynomials. And for the third one, when we've got that division, again, we shouldn't have to show that same long division. It's exactly what we have up on the top. But when we got that division and we know what that long division is, and I want to be able to show my remainder part the same way that I did over here, I'm going to have this written out as 2x squared plus 5x plus 2, and then that remainder of 3 I would have as 3 over the divisor was x plus 1. Okay, that last one that we had there with that fraction, that rational leftover part, that's what we're going to be looking at today. Okay. In 2000, the Environmental Protection Agency, the EPA, reported a combined fuel efficiency for cars that assumes 55% of city driving and 45% of highway driving. That's just saying most people are driving their cars 55% on the highway, 55% in the city, 45% on the highway. So they took that and they wrote this formula. Basically, they've got 100 times x times h. X is going to be the city driving and h is the highway driving, and they have the denominator is 55 times x plus 45 times h. They've got that whole formula. That's the formula that we're going to be using. So several conventional cars have a fuel economy for highway driving that is about 10 miles per hour, or 10 miles per gallon higher than for city driving. So the h that we're going to use is the x plus 10. So we've been doing some of these problems where we can do a substitution. So instead of having multiple variables, we can take the h out of there and replace the h with an x plus 10, trying to get a fewer number of variables in our problem. So we're going to write this function so that it's all in terms of x. Okay. So what we're going to do here is we're going to take this right here. We're going to do a substitution. Instead of the h, we're going to put in an x plus 10. So my original problem, we have 100 xh over 55 x plus 45h. I'm going to write that as 100 x, and then instead of h, I'm going to put x plus 10, and 55 x plus 45, and then instead of h, x plus 10. And then we're just going to clean this up a little bit, right? We can distribute in the numerator. We can have 100x times x would be 100x squared. And 100x times 10 would be 1,000 x. And in the denominator, when I'm actually going to write this underneath here, if I would distribute that 45, I would have 45x right here plus 450. And then I can combine these x's. I have 55x and 45x. That's actually 100x plus 450. So now everything's in terms of x. Okay? And that's all they were asking for in that. I could look at maybe trying to simplify that, maybe try to divide everything by 10 because everything has a 0 in there, but that's all they really wanted us to do. Then this says for number 2, write this function, and this says this is supposed to be function f, so I really probably should have said that this is f of x equals all of that mess. Write that f function in this form. This is what we're doing today. They want us to do this division so I can have the division part. So do some division so I can get this part, and then the remainder part goes over the original divisor, right? They want us to just kind of try to clean this up as much as I can. So here's what we have to do. This is going to be some division. I'm going to do this as a long division instead of one of our diagrams. I'm going to have 100x plus 450 100x squared plus 1000x. So my first question would just be, how many times, and I should probably have a plus 0 at the end here, so I've got a linear term. How many times, or what do I have to multiply 100x times to get to 100x squared? Well, I would only have to multiply by x. So x times all of this would be 100x squared plus 450x. Now I do my subtraction, and we would add the opposite. So my x squareds cancel. 1000x minus 450x is going to be 550x. We bring this down, plus 0. So what do I have to multiply 100x times to get to 550x? Now that's kind of weird because we haven't had to do this before, but because it's 100, it's not too hard to say I'd have to multiply by 5.5. That first one is pretty nice. That's just going to be 550x plus 5.5 times 450 is really 2,475. Good thing I did that ahead of time. 2475. And we would subtract, add the opposite. So my x's go away. 0 plus a negative 2475 is negative 2475. And keeping in mind how they want this answer to look, they want it to look like this. They want a polynomial function, which is going to be my x plus 5.5. And then they want the remainder, that negative 2475, to go over the divisor. So I would say that f of x, pick a new color, f of x equals x plus 5.5, that's what I got when I divided, minus, or I could just have a negative there, 2475 over that divisor, 100x plus 450. And one more thing that I could do is I can clean up that fraction part. I know that having a decimal in a fraction is maybe not what we're exactly used to, but I can look at that 100x and the 450 and say I could divide both of those numbers by 20. And if I would divide, actually by 50, let's divide them both by 50. That'll give me a decimal in the numerator, I know, but it'll clean it up nicely. X plus 5.5. Dividing by 50, I would get 2x plus 9. That denominator is nice. The numerator, we're going to get a decimal. It's 49.5. That's not so bad, though. Okay. So that's how we're writing our final answers for these rational functions, right? We want to have our division, and then the extra part, the leftover part or the remainder goes over the divisor. So in this table, if I were here with you in class today, I would split you into groups and say each group is going to do 1 or 2 of these and we'll share our answers. Unfortunately, since I'm not there, you just have to listen to me, I'm sorry. What we're asking for here though is for each of these different functions, I want to know the degree of the numerator and the degree of the denominator first, because that will help to determine what our graph will look like for our end behavior. That'll help us figure out the asymptotes. We love that word. So let's start with the first one. For the degree of the numerator, since I don't have a variable in the numerator, that degree is 0. The degree of the denominator, since it just has an x, that has a degree of 1. Okay. When I would try to do that division, because I would have just a 5 in the inside of the division, and the x plus 2 is on the outside, that's the divisor, a bigger exponent on the outside, can't really do that. I would just have a 0 when I do my division, and I would subtract, and I would just have a negative 5, which is what I have right now, over, like, this thing doesn't change. It's just going to be x plus 2, right? The 0 is like the whole number part, don't have anything. What we would have talked about already is that if I have a bigger degree in the denominator, the end behavior is that the asymptote is going to be, the graph will be approaching y equals 0. Okay, that's a horizontal asymptote. When y equals 0, that means that that graph is kind of leveling out along the x-axis. All right, for the next one, for the h of x graph, 7x minus 5 over x plus 2. The degree of the numerator is 1 because it's x to the first power. The degree of the denominator, also 1. I'm going to have to actually do this division though. So you have some space down at the bottom where it says, are you ready for more? Feel free to actually do this division yourself. I'm going to have to just kind of zoom up here a little bit. I've got x plus 2 is my divisor for all of these. X plus 2 and 7x minus 5. So x goes into 7x 7 times. So I would have 7x plus 14. And we subtract, and we would add the opposite. When I do that, my x's are going to go away, but negative 5 and negative 14 is negative 19. So that means that negative 19 would be my remainder. I would have a negative 19 over my divisor, which is x plus 2. That's how I'm going to write this. I would have 7 minus 19 over x plus 2. For the end behavior, this is going to approach this part right here. It's going to approach y equals 7. All right, for the j function, the degree of the numerator is 2 because we've got a power of 2. Degree of the denominator is 1. So we've got a larger exponent in the numerator. We're going to have to do our division here also. I've got 3x squared plus 7x minus 5, and we're going to divide by x plus 2. When I do that division, I have to, again, ask, what do I have to multiply x times to get 3x squared? And that's 3x. So that would give me, I look down, that would give me 3x squared, and 3x times 2 would be 6x. So I would subtract, and add the opposite. So x squareds go away. 7x, negative 6x, 1x. So then when I ask, what do I have to multiply x times to get 1x? Well, that's just 1. So I'm going to bring down this. I forgot to bring down the 5 right away. I'm sorry. 1 times x plus 2 is just going to be 1x plus 2. So I'll subtract. Add the opposite. And my x's go away, and I'll have a negative 7 left over. So I will have negative 7 over x plus 2 as that remainder. So I've got 3x plus 1 and negative 7 over x plus 2. So this one, my asymptote is not going to be just a vertical or a horizontal. This is going to be approaching y equals 3x plus 1. Okay, we have one more that we have to do our division on here. Yeah, all right, let's do another division. So, I'm hoping that maybe you can just trust me on the division just to save some time. I did the division. I hope that you can trust me on this. But the degree in the numerator is 3. The degree in the denominator is 1. When I did my division, I got 2x squared minus x plus 9, and my remainder was a negative 23. So it'll be a negative 23 over x plus 2. And again, that means that the line is going to be approaching, or my graph is approaching (2x squared minus x plus 9), right? Which is a quadratic. That's going to be a curved line. In the last one, we're not actually going to need to do a division for the m function. The degree of the numerator is 1. The degree of the denominator is 3. When the degree in the denominator is bigger, remember, that saves us a whole bunch of work. That means that it's going to be approaching because if I tried to do that division, I would have that numerator divided by the denominator is going to be 0 minus that whole mess that I have, actually plus that whole mess that I have right there. X plus 2 over 2x cubed plus 3x squared plus 7x minus 5. Right? I don't have to do that division because I can't do that division. There's nothing to do there. So there's my table. What we notice about the end behavior here is that if the denominator has a bigger degree, it's going to approach y equals 0. If it has a bigger degree in the numerator, then we've got some other stuff that we have to look at. What this is going to ask you to do for the are you ready for more, and I just have this graphed, it asks you to look at that J function. Here's what it looks like. Oh, I'm holding my pen. Looks like this. There's a vertical asymptote, but it also has the asymptote of y equals 3x plus 1, so that the vertical asymptote is right here, but y equals 3x plus 1 is right here. That wasn't very straight line, but those two asymptotes give me 2 lines that my graph can approach. That's how I've got those 2 different curved lines. Okay. Number 2 says, under what conditions would the end behavior of a graph of a rational function approach a line that's not horizontal? That's any time that the denominator has a degree that's more than the numerator. And we're just going to skip number 3 because I'm not there. Whoop. This is back to our cylinder discussion, and I think that I have already talked more than enough. So we're just gonna move on. You do have an assignment today in your journal, so please make sure that you do those problems, and then you also have a formative today. Hopefully you can do a good job on that and listen to whoever your sub is. And if you need any help, send me an email. Thanks.